We're going to talk about section 7.7 in our book on identities. So an identity is something that's true for all values of x. So our most famous identity in trig is called the Pythagorean identity, and that's sine squared plus cosine squared equals 1. So from that, we can also get a couple of derivations of that. We could subtract the cosine squared to the other side and get that sine squared is 1 minus cosine squared x, or we could subtract the sine squared to the other side and get cosine squared x is equal to 1 minus sine squared x. These are common enough that we want to be able to recognize those and just kind of know them as a matter of course, so that we can replace a sine squared by 1 minus cosine squared, or if we see a 1 minus sine squared, we know that that's the same thing as a cosine squared. Now, we can also get a couple other derivations of this. If we start with our basic identity, our sine squared plus cosine squared equals 1. If we divide through everything by cosine squared, we're going to get another version of this Pythagorean identity. So the sine squared over cosine squared is a tangent squared x, and whoops, I don't want to call that equals. A cosine squared over cosine squared is 1, and a 1 over cosine squared is secant squared x. So there's this identity, or the different versions of it. So here we have that secant squared is equal to tangent squared x plus 1. We could also say that tangent squared x is secant squared x minus 1. And so we can trade one in for another, and sometimes that's helpful or useful. And the other important Pythagorean identity is it comes again from sine squared over plus cosine squared equals 1. Instead of dividing by cosine squared like we did the last time, we can divide through by sine squared. And so then we get a sine squared over sine squared is 1. Cosine squared divided by sine squared is a cotangent squared x, and 1 over sine squared is a cosecant squared x. So you can see that cosecant squared x is the same as cotangent squared x plus 1, and similarly cotangent squared x is cosecant squared x minus 1. These come in useful a lot of times in trig, but also next year in calculus as well. And so we want to kind of learn to recognize them. We see that the cotangent squared and the cosecant squared are paired together because they both have that denominator of sine squared. Likewise, a secant squared and a tangent squared often go together because they are unified by this common denominator of cosine squared. So some ways we might use this just for a little practice here. So to simplify tangent x times cosine x, we can rewrite tangent x as sine x over cosine x, because that's what a tangent is. That is multiplying that cosine x. When we kind of decompose that tangent x into sine over cosine, we can then cancel the cosines and see that really tangent x times cosine x is the same thing as sine x. That's a simplified version of that. Now, the 1 minus cosine squared x, if you recall, hopefully that's ringing a bell, we said earlier that 1 minus cosine squared x is the same thing as sine squared x. That is true because it comes from our most famous trig identity, sine squared plus cosine squared x equals 1. So we can replace that 1 minus cosine squared x by a sine x. Then we can cancel a sine x out of each of those, and this then can be simplified to sine x. That's a simplified version of that. Okay, I'm going to slide the screen up. Looking at the blue one here, if we square out this binomial here, we will get, remember, it's going to be the first one squared twice the product plus the second one squared. So there's the first term squared, twice the product is going to be 2 sine x times cosine x, plus the second term squared is going to be cosine squared x. And then we still have this minus 2 sine x cosine x waiting in the wings. So we can recognize, hopefully, that the 2 sine x and the negative 2 sine x will cancel each other out. And then hopefully we recognize our most famous of all trig identities, sine squared plus cosine squared x is equal to 1. So that whole expression simplifies to be just 1. Okay, looking at some other identities here. So if we recall the graphs of y equals sine x and y equals cosine x, you can see them to the right here. The yellow curve is our sine x. It starts in the middle, and we do loop above, loop below. It goes on and on and on forever. We can see the cosine x as the green function. It starts big and does that half loop above, loop below, and then goes on and on and on forever. Now, when you look at those, you can see them as translations of each other. So if we start with that sine x, and if you look at that yellow curve, if you were to move that yellow curve, remember now this is pi over 2 right here. If we move the yellow curve pi over 2 to the left, it would be a perfect fit for the cosine curve. That is, if we did sine of, and to move that left pi over 2, we would go x plus pi over 2. That would be exactly equal to a cosine curve. And so this is an identity, that the sine of x plus pi over 2 is equal to the cosine of x. By the same token, if you look at the green curve, the cosine curve, if you were to move it pi over 2 to the right, it would be a perfect fit for the sine curve. That is, to move something to the right pi over 2 means we translate it pi over 2 to the right, then we can see that the cosine of x minus pi over 2 is equal to the sine of x. So these are also another pair of identities. Okay, I'm going to move the screen up. Now we have what are known as the cofunction identities. So these are where the names come from: sine, cosine, secant, cosecant, tangent, cotangent. So the cofunctions are related to each other by the cosine of an angle is the sine of its complement. So if you look at a right triangle, and you can see the green triangle below, if we have an angle theta, then I guess I should call that, instead of pi over 2 minus x, let me call that a pi over 2 minus theta, since I named that as a theta. I'm going to bring my pen back. So that's really pi over 2 minus theta. So these two angles are complements of each other. They're going to add up to be 90 because we already have a 90 degrees taken up for the right angle. And the sum of the angles in a triangle is 180. So you can see that the cosine of this angle theta would be the adjacent over the hypotenuse, which if you look at its complement, the pi over 2 minus theta, then that's the same as the opposite over the hypotenuse. And so we have that the cosine of one angle is the sine of its complement. And the same is true if we switch around the role of sine and cosine. That also works for the secant and the cosecant. Remember, the cosecant is the reciprocal of sine. Sine is opposite over hypotenuse, so the cosecant is going to be the hypotenuse over the opposite. So if we look at this angle theta, the hypotenuse over the opposite, and then we switch to the other angle, its complement, that's the same as the adjacent over the hypotenuse, which is going to make that be the secant. And it's true for the tangent and cotangent as well. So those are known as the cofunction identities. So for example, we know that the cotangent of 20 degrees would be the same as the tangent of its complement, which would be 90 minus 20 would be 70 degrees. Okay, that's what we mean by the cofunction identities. Okay, so let's see if we can use what we know here to find the values of the other 5 trig functions if we're given one of them. So we're going to draw a triangle here. So if we have an angle in quadrant 1, so I'm going to draw an angle in quadrant 1, and I'll make it part of a right triangle. If the sine of that angle is 1/3, that means that the opposite over the hypotenuse is going to be 1/3. Using Pythagorean theorem, we can say, if I call this side A for a moment, that c squared, that's going to be 9, is going to be a squared plus 1 squared. So the a squared is going to be 9 minus 1 is 8. So a will be the square root of 8, which we can think of as 4 times 2 is 2 square root of 2. So that means this adjacent side is going to be 2 square root of 2. So now we can get all of the other trig functions. So we can say now the cosine of that angle theta using our SOHCAHTOA is going to be the adjacent. That's 2 over square root of 2 over the hypotenuse. The tangent, we can say, is going to be opposite over adjacent. So that's going to be a 1 over 2 square root of 2. We'll be expected to rationalize that. So that's going to be a square root of 2 over square root of 2 times square root of 2 is 2 times the other 2 is 4. We know that the cosecant of theta is the reciprocal of the sine. Since our sine was 1/3, that's going to make the cosecant be 3 over 1, or 3. The secant of theta is the reciprocal of the cosine, and since the cosine was 2 square root of 2 over 3, the secant will be 3 over 2 square root of 2. Of course, we're going to have to rationalize that, so that's going to be 3 square root of 2 over, and again, square root of 2 times square root of 2 is 2 times the 2 is 4. The cotangent of theta, I think it's easiest to think of that as the reciprocal of tangent theta. Since tangent theta is square root of 2 over 4, I'm going to go back to it before we rationalized it. So I'm going to look at tangent theta as being 1 over 2 square root of 2. So its reciprocal will be 2 square root of 2 over 1, or just a 2 square root of 2. Okay? Let's see how that looks when we move into other quadrants. So now we're going to look at quadrant 3. So we're going to draw our reference angle, our reference triangle in quadrant 3. The cosine is the adjacent over the hypotenuse. And the hypotenuse is always positive, so then we know that the adjacent must be the -2. If I call this a for a moment, we can use Pythagorean theorem and say 3 squared is a squared plus -2 squared. So 9 is a squared plus 4. So a squared is 5. So a is going to be the square root of 5. Because we're in quadrant 3, that's going to have to be a negative square root of 5. See how that works? Okay, so now we know that I'm going to rewrite over here. The cosine of theta is -2/3. So the sine of theta is going to be opposite over hypotenuse. That's going to be a negative square root of 5 over 3. The tangent of theta is going to be opposite over adjacent. So that's going to be a negative square root of 5 over a -2. The two negatives will cancel, so we'll get square root of 5 over 2. Now we can get the reciprocals. So the secant of theta is the reciprocal of cosine, so that's going to be a -3/2. The cosecant of theta is the reciprocal of sine, so that's going to be a -3 over square root of 5. We're going to have to rationalize that and call that -3 square root of 5 over 5. The cotangent of theta is the reciprocal of tangent, and so that's going to be a 2 over square root of 5, and we'll rationalize that as well to get to 2 square root of 5 over 5. Okay, let's try one more. We've got tangent of theta is negative 4/3, and now we're going to be in quadrant 4. So we'll start by drawing our reference triangle in quadrant 4. Tangent we know is opposite. Oops, I bumped that with my hand, is opposite over adjacent. So that's going to be, I got to bring my pen back up. So that's going to be 4/3, and because we're in quadrant 4, we're going to have to make the opposite side be the negative. We can do a little Pythagorean theorem. 3 squared is 9, 4 squared is 16, 9 plus 16 is 25, square root of 25 is 5. So our hypotenuse is 5, and the hypotenuse is always positive. So we can now say sine theta is going to be opposite over hypotenuse. Cosine of theta is going to be the adjacent over the hypotenuse. We were given the tangent of theta is negative 4/3. We can do their reciprocals. The cosecant of theta will be a negative 5/4. The secant of theta is going to be 5/3. And the cotangent of theta is going to be a negative 3/4. Okay. Now we take the same idea that we've just been doing, but we add maybe a layer of complication in that we're going to see that instead of just a sine or a cosine or a tangent or whatever given as a number, it's going to have an x in it. This comes up in calculus next year. So we are still going to do the same idea. We're going to draw a reference triangle. We will always assume given variables, unless it's specifically noted otherwise, the assumption is that the angle is going to be in quadrant 1. It's complicated enough with these variables in there, and we won't add to that complication by placing it into a different quadrant. So the sine of theta is opposite over hypotenuse, so that means we're going to label the sides of the triangle this way. We need to figure out what this other side is. I'm going to call it a for a moment. We can use our Pythagorean theorem and say a squared plus x squared is equal to 3 squared. We're going to solve this for a, so we're going to get 9 minus x squared, subtracting that x squared to the other side. We're going to square root that and get the square root of 9 minus x squared. Now, you could theoretically say plus or minus, but we're assuming here in quadrant 1 everything's going to be positive, so this is going to be positive. Now, don't resist the temptation. You cannot distribute that radical. You cannot say that's equal to 3 minus x. That is not true. But we can now say that this adjacent side, although it may seem kind of weird and kind of complicated, it's going to be that square root of 9 minus x squared. Now we can find whatever trig function we want. In this case, we're asked for the tangent of theta, and from SOHCAHTOA, we know that tangent is opposite over adjacent, so that's going to make that be x over the square root of 9 minus x squared, and that's our answer. Okay, maybe look like a mess, but that will actually serve a purpose next year. That'll be useful. Let's try it with a different trig function. So now we have the cosine of theta is 2 over x. So we'll draw our reference triangle always in quadrant 1. So there's our theta. And cosine we know is adjacent over the hypotenuse. So this time the x is in the hypotenuse. We'll call that a for a moment. Using Pythagorean theorem, we will try to solve for that missing side length. So in this case, we're going to get a squared is x squared minus 4, and so the a is going to be the square root of x squared minus 4. So the cosecant is going to be, now the tangent is opposite over hypotenuse, so the cosecant is going to be the hypotenuse x over the opposite, which is that square root of x squared minus 4 that we just found. Okay? And finally, we'll look at a tangent. So same idea, drawing our reference triangle in quadrant 1, and knowing that the tangent from SOHCAHTOA, get my pen back up, the tangent is opposite over adjacent. We can use the Pythagorean theorem and say c squared is going to be x squared plus 5 squared. So c is going to be the square root of x squared plus 25. So I will call that hypotenuse the square root of x squared plus 25. So that's going to make the cosine be the adjacent 5 over the hypotenuse square root of x squared plus 25. Oh, and I should mention, I didn't mention that earlier, I just did it. When we have variables in the denominator, we will not try to rationalize. It just gets too messy. So our general rule is if we have a number in the denominator, in the radical in the denominator, like we did on some of these, we will be expected to rationalize. But when we get variables in the radical in the denominator, we will not rationalize. All right, very good.